with that, I will close this introduction and start to give the floor to our first speaker, John LaBrecque. John LaBrecque is a chair of the IUGG Commission on Geophysical Risk and Sustainability, as well as the lead of the GGOS Geohazards Monitoring Focus Area. He is a research fellow at the University of Texas at Austin, and while he was serving as lead of NASA's Earth Surface and Interior Focus Area for 21 years, he oversaw NASA's research and application programs in geodesy and space geodesy. He received NASA's Exceptional Service Medal and multiple distinguished awards from the American Geophysical Union and the Institute of Navigation. Now yielding the floor to John.
Thank you, Leo, and thank you to the IGS Central Bureau for providing this opportunity for discussion on GNSS early warning systems. I also wish to thank Elizabeth D'Anastasio, Siddhartha Krishnamurthy, and Timothy Melbourne for their contributions to this presentation. The left-hand illustration was generated by the Global Geodetic Observing System several years ago to highlight the advantages of the application of geodesy to environmental monitoring and geohazards. In this discussion, we will focus upon tsunami early warning systems, or GTEWS as we might call them, that consist of networks of properly positioned GNSS receivers that broadcast data in real time on ground displacement and ionospheric dynamics. The real-time data are coupled to an analysis system that provides the essential data for the issuance of appropriate warnings. On the lower right-hand side in the illustration, we see on the left an illustration of what we might expect from a properly operating GTEWS network. These were recorded by the Japanese GeoNet system network and records the Tohoku Oki earthquake during the disaster of 2011. In red, you see the total ground displacement recorded by the 1,200 receivers. On the right-hand side, you see the resultant impact of the displacement of both ground and ocean upon the ionosphere. From this, we learned that GTEWS could provide not only warning, but also verification, validation, and tracking of any resulting tsunami. GTEWS depends in large part upon the international investments in navigation satellite systems, both global and regional in character. On the lower right-hand side, we see a Mercator map of the distribution of what we might expect for all in view satellites at any particular point. The red illustrates the contributions of the QZSS and NAVIC systems and overlaying the global satellite observations. The higher density in red features up to 35 satellites in view at any particular point beneath those areas versus 10 or so in the remaining areas. The importance of increased satellite observations, all in view observations, adds to the accuracy of ground displacement estimates, as well as the fidelity of our imaging of ionospheric response. GTEWS owes its initial concepts to a terrific and horrific disaster, which was the great Sumatran earthquake, followed by the Indian Ocean tsunami that claimed over 200,000 lives in 2004. What we learned from that is that we could have utilized the GNSS data to provide real-time, nearly real-time, within 15 minutes, an estimate of the magnitude of that Sumatran earthquake that would have required the issuance of tsunami warnings. Unfortunately, there was no such estimation and no such warning, and many lives were lost. In 2011, as we discussed in the previous slide, the Tohoku Oki earthquake and the Japanese GeoNet network recorded the ground displacements and subsequent ionospheric displacements, which really expanded the role that GTEWS might play in tsunami warning. In 2015, the IUGG General Assembly, in resolution number 4, called for its membership to support the development of an Indo-Pacific effort to implement GNSS augmentations to tsunami warning capabilities. In 2016, the Global Geodetic Observing System of the IIG issued a call for participation in a working group to support resolution number 4. That group now numbers 18 organizations from 12 nations. In 2017, that working group supported the development of the GTEWS 2017 workshop, which reviewed the maturity and utility of GTEWS and provided recommendations for its development. The report was published in 2019 by the UN Office for Disaster Risk Reduction in its Global Assessment Report, and also by the Association of Pacific Rim Universities. One of the principal recommendations of the report was to organize a consortium of principals, those folks most supportive of the development of GTEWS in both resources and interest. And we hope to use that concept in the development of a GTEWS Oceania later in this discussion. GTEWS utilizes displacement as TE and total electron content, as discussed earlier. The networks provide real-time GNSS data to a capable analysis system that employs finite fault models to determine magnitude and crustal displacement, and that information is also imparted to tsunami modeling algorithms to estimate the magnitude and distribution of a resulting tsunami. These data are available in about 5 minutes time from the initial earthquake displacement, and as we improve computer capabilities, that time should be diminished. On the right-hand side, you see the importance of total electron content measurements because they serve to both provide verification of the predictions and validation of the observations, And finally, tracking of the data, the tsunami propagation as it progresses across a particular ocean basin. TEC is derived along the path of propagation from satellite to the ground receivers, where that path of propagation crosses the ionosphere. It's called a piercing point. And as we multiply the numbers of satellites and the numbers of ground stations, we multiply the numbers of piercing points and therefore increase the fidelity of the estimation of ionization disruption. The ionization disruption is caused by the uplift of the ocean surface in response to ground displacements. This uplift creates a pressure wave system that pushes aside, disrupts the ionization in the atmosphere. These would be measured in real time through the TEC estimates along the ray paths to the satellites. On the right-hand side, we see the results of the Tohoku Oki earthquake as measured by GeoNet. The initial black at initiation, the dark blue at initiation, really is thought by some to provide a means of estimating the magnitude of a nascent tsunami, as well as the propagation of waves, as you can see following that that dark blue center of initiation. Requirements to achieve Pacific GTEWS. First and foremost, we need international collaboration to, one, provide political support as well as data and software sharing. Improved GNSS network infrastructure involving real-time multi-GNSS receivers as well as active maintenance. Regional broadband access to provide real-time access to connection between data centers and networks. Satellite broadband may also serve extremely important roles in remote areas. Integrated computational infrastructure, national and regional analysis enhanced by cloud computing, and finally, persistence. We need to maintain the operation of these GTEWS networks because these extreme events occur seldom during the period of a decade, maybe 8 or 10 such events, and we need to ensure that the networks continue to operate properly. We rely upon GNSS receiver distributions, especially the real-time distribution. On the upper right illustration, you see all of the available GNSS data for the globe. Currently, it measures over 20,000 such receivers. Unfortunately, less than 1 in 8 of those receivers are available to the community and stream in real time. Particularly apparent is the lack of data within the Oceania region and the Western Pacific, as well as the northern South American continent, although these data should be available soon. How many receivers would be needed for a GTEWS-PACIFIC network? The estimate is about 1,700. These can be utilized from currently operating real-time GNSS stations or upgrading those that don't quite meet multi-GNSS real-time streaming capability. We also need a within that 1,700 or about 500 or so TEC monitoring receivers randomly distributed throughout the basin. They do not need to be geodetic quality, but they should be multi-GNSS real-time streaming systems. They could be on ships, they could be on islands, etc. There are two real-time analysis capabilities that I know of. The first is the GPSCOCKPIT, which provides real-time displacement monitoring as well as tsunami warning. And the second will be shown subsequently that provides TEC monitoring. The GPSCOCKPIT is provided by Central Washington University with Tim Melbourne as lead. And here you see the area of Oceania with the highly developed and well-functioning New Zealand and Australian networks. And notice that the area of Oceania is very sparsely populated, as is the Western Pacific. The Guardian real-time network from JPL was displayed in the opening comments by Leo. Here we see the Hunga Tonga eruption, and without repeating Leo's comments, you notice that here the yellow regions are those data recorded by the New Zealand and Australian networks, but largely the illustration is in pink due to the requirement of utilizing the global ionospheric model. There are a couple of things to note here. First is that the distribution of tsunamis in this region is a bit confused, and therefore very important to monitor the incoming waves, because they involve very high oceanic relief, which changes the velocity distribution of tsunamis as well as associated reflections. Most importantly here is that if we combine all observed GNSS data, we arrive at this travel time curve for ionospheric disturbances. And you see by the very vertical nature of these systems, and subsequently farther out in time and space, we observe a slowing, somewhat slowing. These are explained by the USGS modeling referred to below. USGS observed that the tsunami was generated by an air pressure wave from the explosion, and that propelled a very rapidly propagating tsunami at about 700 kilometers per hour. And it is an example of a medio tsunami that only bottom pressure measurements and GNSS tsunami techniques have succeeded in monitoring the propagation of these events. In review, basically, the technology is in hand, and the analysis algorithms are in hand. What is lacking is the optimization of the proper GNSS networks and international agreements, etc. We hope to make advances in the development of G2s, and we propose here that we a G2s Oceania that would act as a prototype network for the global community, not only to provide essential services to G2s, but to serve as an example of international collaboration. This serves to outline our concerns in this area. And in concluding, we wish to announce the organization of a series of Zoom meetings beginning March 1st at 1 p.m. New Zealand time to begin to discuss the development of a G2s Oceania. All are welcome to participate. Thank you very much. And oh, by the way, please to register for news on these discussions, please register your intentions at my email, j.labrecque@mac.com, with the subject area G2s Oceania. Thank you.
Thank you very much, John. We'll keep any questions for John to the end of this workshop. And again, you can most likely contact him by email.